Hi guys, today we are going to wrap up our discussion in chapter 11 by talking about things like refrigerators and air conditioners, and then we're going to segue into talking about the second law of thermodynamics, which is the law of entropy. So when you have a refrigerator, the air inside of it is much cooler than the air outside or in your surrounding kitchen. So every time you open the door to your fridge, what's happening is that heat is flowing from the warmer air in your kitchen into your refrigerator. But the purpose of a refrigerator is to keep everything cool. So what a refrigerator needs to do is to remove that excess heat back out into the warmer room. So transferring the heat from a cold reservoir to a hot one is the opposite of what should naturally happen. And in order to do that, you need to have a heat pump. So with the heat pump, it will put work into the system to remove that excess warm air and put it back into an already warm reservoir, which is what it doesn't want to do. Heaters work the same way, moving thermal energy from outside the house to the inside. So in all of these cases, energy still has to be conserved. So our laws of thermodynamics can't really be violated. It just requires an energy input or work to be done. So here is your warm reservoir is equal to the temperature or the heat of the cold one plus the work done. So for heat pumps, instead of computing machine efficiency, what we're going to be doing is calculating something called coefficient of performance. So there's two different coefficients of performance depending upon whether you are looking at a heat pump used for cooling, which is what the top one is, or a heat pump used for heating, which is what the bottom one is. And the formula is essentially the same. It's just what is the temperature of your cold reservoir on the top for the cold one, and what is the temperature of your hot reservoir on the top for the one that heats. Remember when we talked about the efficiency of heat engines, the efficiency was typically less than 1, right? If it was 1, then that meant that you had 100% efficiency, and that's impossible. But heat engines, because you are doing work on the system, because you are putting energy back into it, the COPs, or the coefficients of performances for these guys, will typically be more than 1. So now we're going to talk a little bit about the second law of thermodynamics, or the idea of entropy. And you guys have probably heard of entropy before, but you may not know exactly what it means. The second law of thermodynamics has been stated a lot of different ways in a lot of different textbooks, but it has three main ideas, and they all kind of mean the same thing. The first idea is that heat always flows from hot body to a cold body. The second thing is that nothing is 100% efficient, which we've already talked about 1 and 2. The third way to discuss the law of thermodynamics is to talk about entropy. The entropy of an isolated system never decreases. It will either increase until the system reaches equilibrium, or it will stay the same if the system was already in equilibrium. So that term isolated is really important, right? Isolated systems are ones in which no work is done on it, or nothing is put into the system to change it or rearrange it. So let's take a look at kind of what that looks like. This is a funny little comic for you guys. So entropy is considered to be the amount of disorder that's in a system. So natural processes tend to move towards a state of greater disorder. So what that means is that if I take all of these gas molecules and I place them in this configuration over here on the right, given time, eventually this configuration would spread out and appear to be more disordered. The entropy of the system would increase. You will never get the reverse, right? The gas molecules that are floating around free in the room will never all of a sudden spontaneously form this configuration over here on the right. And this kind of goes back into what I was talking about, isolated system. In order for the gas molecules to go the other way, to go from being all spread out to very compact, I would need to do something to the system. I would need to apply a force to the gas molecules, or I would need to put work into it, or I would need to make this configuration over here, which makes the system no longer isolated the minute that I start adding that into it. So here's another example of entropy If you tossed bricks off of a truck, what kind of pile of bricks would you most likely produce? Probably the one over here on the right. They will probably, highly unlikely that they will form this perfect structure that they show in this picture over here on the left. So for all real situations, meaning isolated, the change in entropy is typically greater than 0. Like I said, there are some cases where the entropy will stay the same, and those are for systems that are already in equilibrium. So looking at an ice cube, another graphic here, ice cube has very small entropy because it is very ordered, but given time, the ice will melt and it will achieve a state of more entropy with minimum order. So there is a way to calculate entropy, but we don't really get into that here, just really understand the concept of it. Another example is to say a solid coffee cup is a more orderly object than pieces of a broken one. So if you drop a coffee cup on the ground, it will probably shatter into a million pieces. If you drop those pieces on the ground, they will never spontaneously come back together as a coffee cup. Things always progress to a state of more disorder naturally in the universe. So when another form of energy is converted into thermal, what you do is you increase the entropy. So only thermal energy is associated with entropy. All other forms of energy are what we call ordered. So let's look at an example of what that is. So in AP1, we probably you guys talked about the idea of converting kinetic energy to potential. So as you throw a ball upward, the kinetic energy converts to potential energy, then it comes back to kinetic as it falls back down to the ground. This is an ordered system, and the entropy of that system remains constant because in this particular situation, there is no thermal energy happening. But if I let that ball hit the ground, and the ball bounces on the ground a few times and then comes to a stop, well, it's lost some energy due to thermal energy. The ground has gotten warmed up, the ball has maybe gotten warmed up as it bounces, and that process is irreversible. So that means that entropy has increased. The energy has gone from kinetic and into a thermal energy situation. So you will never see the ball cool off and spontaneously jump back up into the air, right? That's what we mean by irreversible process. The ball bounces a couple of times and it stops. It never all of a sudden starts bouncing and flies back up into the air and cools off. So that would conserve energy, but it would reduce the entropy. So that violates the second law of thermodynamics. So you never see that happening. So this is just a quick little check for you guys. Read through this and then bring your answer tomorrow to class, and we will talk about which one you thought it was and why. The last little thing I want to discuss with you guys, though, is just the idea of entropy in terms of heat death. So some scientists, mathematicians, astronomers predict that the universe, the fate of the universe, is what they call heat death. And what that means is that all of our energy available to us in the universe has been transferred to thermal energy. So thermal energy is less useful for us. We can't really do anything with it. We can't do work with it. It causes entropy to increase. And so if all the available energy to us gets transferred into thermal, then the universe will approach a state of maximum disorder. So maximum disorder means that there is a large change in thermal energy, and when the thermal energy increases, there is no availability or no possibility for us to use it. So luckily it's a really long way off if it happens at all. It is just a theory out there that has to do with entropy and thermal energy. So the last little thing they talk about in your textbook is this idea of conserving energy. So this whole chapter we've been talking about how we use it. And you guys have probably been told to conserve energy, drive less, turn off our lights, turn down our thermostats. But first law of thermo says energy can't be created or destroyed. So how do we conserve it exactly? How can there be an energy crisis if energy can't be destroyed? So it's important to know that we can't really run out of energy, but what we're running out of is energy that we can use, kind of like what I talked about before. Your car is a really good example. So as your car burns gasoline, it's changing its energy from chemical into thermal. And that thermal energy that gets dissipated is useless to us. We can't use it to power anything or use it to do any work. So these constant energy transfers are decreasing the supply of high quality energy to us. It's increasing our entropy. So a better way to think about it is to conserve energy and concentrate more on making things more efficient. So more efficient light bulbs, more efficient cars. All of these things use less energy and they produce the same result. All right, that's it for tonight. I will see you guys tomorrow.